what we're going to do is we're going to go back to when we first started the chapter out, chapter 6, and we talked about these things called polar bonds, nonpolar bonds, covalent bonds, and ionic. If you have your notes available, chapter 6, we started going over those three divisions, and you guys handed an assignment in on it. So I'm going to give you 4 bonds, and I want you to tell me if they're polar covalent, nonpolar covalent, or ionic. Okay? So here are the combinations. So, on the back of the periodic table, there is a chart, if you remember, that gives the electronegativities. It's the top right-hand number of your periodic table. And those are your electronegativities. If you have a book, those electronegativities will be located in the last chapter, chapter 5. You need to have that. You don't have your periodic table available, then you can get those electronegativities off of page 161 in your book. Page 161 in your book, you can get them. So let me give you a minute. Do your subtraction, your difference, and then we'll determine if they're ionic, molecular, or ionic, polar covalent, or non-polar covalent.
What number on this do we subtracted in?
The highest and the lowest.
No,
It's just a difference. It's the upper right-hand number. It says electronegativity on the key. What we're going to do is we're going to connect some ideas today and tomorrow and Thursday and Friday. And the ideas we're connecting are the following. We're going to look at mainly polar and nonpolar covalent bonding. Okay? And how that affects this idea that we're going to talk about a lot tomorrow, a little bit today, is intermolecular forces. Intermolecular forces have to take place between molecules. And molecules are individual units that are held together by covalent bonds. Okay? So we'll have to determine which of these 4 would be covalent, and we'll focus on just the covalent and which ones are going to be considered ionic. Okay? Kendall, what'd you get for the first bond between N and H?
0.84.
Alright, so the difference is 0.84, right? Is that what you came up with? Okay, so this is 3.04 on your chart, and this was 2.2. So you had 0.84 difference, and what kind of bond would that be? Polar covalent, non-polar covalent, or ionic? Okay, polar covalent is between what 2 numbers? 100?
0.3.
No. 0.3 and 1.7. Okay? Hopefully that's right in your notes. 0.3 to 1.7 is polar covalent. So this is a polar covalent bond. That's going to be a big part of what we're going to talk about over the next few days. All right? P and H. Alec, what'd you get for P and H?
Got 0.1.
Is it 0.01?
Yeah.
Okay. And then, so that's considered non-polar covalent. Any questions with those two? Okay. Harrison, what did you get for Li and F?
I have ionic.
So you have ionic. Okay. What was Li's electronegativity?
3.
And
No, wait.
The difference is
Sorry.
9.
oh, the difference
is
Plus
3.
3.
difference is 3.
Yeah.
And so 3.98 for fluorine and lithium was 0.98.
Yep.
Okay, so 3 difference, definitely ionic. Very strong ionic characteristic. Okay, and then when you look at strontium, and it's 0.95. And then you look at oxygen, which is 3.44. The difference is going to be, what is it? 2.49. Definitely going to be ionic because it's over 1.7. Okay, so we're not going to concern ourselves with the bottom 2 because we're going to be talking about intermolecular forces between molecules that are interacting with one another. So ionic is taken out of the equation. We don't work with ionic because it doesn't have characteristics of what molecular compounds do. All right? So I'm going to have you practice drawing 2 structures, and then you'll have to tell me what the shape of the structure is going to be. So we're going to get shape in here. Shape is important in determining how these molecules interact. So the 2 we're going to take are pH3 and NH3. Go ahead and draw the structural formula for those 2. And they're going to be identical structures because nitrogen and phosphorus are in the same group, and then hydrogen, of course, they're the same element in both compounds. So draw the structural formulas for those 2. So when you went through and did the structures, one of them, or both of them look like the same. Correct?
You do the 2 dots, the should pairs.
Yep, I want to show those off the center because that helps me with my shape.
Oh, I didn't see them.
Yeah, I do. This doesn't really do a good job of putting them in there. So what was the shape of that? Okay, trigonal pyramidal, both of them would be considered. Trigonal, pyramidal. If we wanted to kind of show what the 3D would kind of look like in a drawing, both of them would look like the following. We'd have P, and then we'd have our 3 legs, our tripod with phosphorus up above, and then nitrogen would be the same way. I mean, it would be identical shape of the structure. Any questions with those 2 drawings? And then how you could kind of manipulate the drawing to represent the shape. So these 2 drawings are exactly like these 2 drawings, but what I'm doing is I'm indicating by drawing it out like that the shape of it. All right? So go back to our original polar and nonpolar covalent bonds. if we're going to show polar covalent bonds, this is how we're going to go ahead and show them in the future. Non-polar covalents we don't have to do anything with in the drawing. But what we're going to do with this drawing is we're going to go ahead, and we can go ahead and put our dots up there for them. What we're going to do is hydrogen was 2.2 and nitrogen is 3.04. The difference is 0.84. So we're always going to draw an arrow toward the element that has a higher electronegativity, from the lower to the higher. So that would be representing a polar bond between those two elements, hydrogen and nitrogen. We're going to do the same on this back element, back hydrogen. We won't make it as long because it's back farther. And then this one on the side will make the same similar drawing as what we did on the left side. Any questions on how I draw those out? So if it's polar, you show an arrow pointing toward the symbol that has a higher electronegativity. Nitrogen is 3.04, hydrogen is 2.2.
So you have to redraw it like that.
Well, this is a way that you would symbolize those polar bonds. Now, when we do phosphorus and hydrogen, we won't show any arrows. And the reason why is because there's no difference in their electronegativities. So it doesn't create a polar bond. So none of these in pH3 would have polar bonds. Okay? None of these in pH3 will have polar bonds. We won't show them because there's no difference in they're nonpolar. So if they're nonpolar, we don't show the arrows. If they're polar, we show the arrows. Okay? Now, what's the significance of showing the arrows, not showing the arrows? If all of these arrows are pointing toward nitrogen, that has nitrogen in all three of these examples has a greater share of the electrons, what's the charge of this top portion going to be? So that area of the molecule, the top portion of the molecule, what's the net charge going to be up there? Negative or positive? That, they have a greater share of the electrons. Electrons are negative charge. So this top portion is going to be negative. Okay? You've got to think of a magnet, north-south side. One side is going to be one magnetic property, the other one's going to be opposite. These are charges. So this bottom side, and a lot of times you can tell by the tail of the arrow. The tail of the arrow tells you with a charge, right? It symbolizes, what does that symbolize?
Positive.
A positive. So this bottom portion is going to be positive. Now let's say that we have a second molecule that we have drawn. We have it drawn the same exact way. So wherever you have one of these molecules, you have trillions and trillions of these molecules. Lots of them. So we're just going to symbolize it the same way as we do the top drawing. Identical.
So you're drawing the arrows up there to simulate what?
The arrows are a way to show that it is an unequal share of electrons. The arrows point to the element that has a greater share of the electrons, which means it's negative. Okay, so if these two molecules decide to interact, will there be an attraction between those two molecules?
Yes.
Okay? Hunter, what in this molecule will be attracted to what portion of the top molecule?
The valence electron.
No?
No, not the valence.
So this is negative up here.
Oh.
That's positive. So
The
where
positive charge would
right? So there's going to be attraction between these two regions, right? You agree with that?
yes.
The positive and the negative. So we got a lot of these floating around. There's an attraction between those two regions, and that's called intermolecular forces due to dipole-dipole interaction. So what do we mean by dipole? Dipole is just a molecule where you have on opposite ends opposite charges. So the bottom of this molecule, the legs, have a positive charge. The top of the molecule has a slightly negative charge. Okay? And so it will be attracted to another molecule like itself that the opposites will attract. And so this is called dipole-dipole interaction. And that's a form of forces of attraction between molecules. They call it intermolecular forces. Dipole-dipole interaction. And that's the first type of intermolecular force of attraction. So let's go back to pH 3. Do we have any dipole-dipole interaction between two molecules of pH 3? What do you think?
No.
No, because they don't have any dipoles. So there's no interaction between these two molecules. So interaction between molecules affect this thing called boiling point and melting point. So if you had to decide between NH3, ammonia, and pH 3, which one of those two would you say would have a higher boiling point? And why? Hunter?
Would it be NH3 because it would take more energy to separate the atoms?
Right. Right. It takes more energy to break free of one another. And so when it goes from a liquid to a gas, they're breaking free of one another. Okay? And so this NH3 would have a higher, based upon just this interaction, because there's two others we're going to talk about tomorrow, but based upon just that interaction, this will tend to evaporate at a lesser rate than pH 3, and also would have a higher boiling point than pH 3. Because pH 3 has no interaction due to dipole-dipole interaction. So that's all I wanted to go through with you today, because we have people missing. They'll be able to get on the computer and check this out. Real simple concept, I think, when you see how everything kind of fits together. Would like you to do some reading for tomorrow, though, those that are here, and to be ready for the discussion tomorrow. And that would be look at page 203 through 207. I think it will help you understand the concepts of intermolecular forces. Intermolecular forces are just forces, they're not bonds, but they're just forces of interaction between molecules, what causes them to interact. Okay? So, would like you to read those pages. The rest of the time, we have a lot of time left. I'm going to write up on the board